We've all been there. You tap a button to buy a flight or send an urgent message, the loading wheel spins, and you get that maddeningly polite pop-up. Oops, something went wrong. Behind that error screen, your app is actually a distributed system. Dozens of individual services constantly talking to each other over a network. And in these environments, network calls fail. Connections drop, APIs stall, and servers time out. Because engineers cannot write code that physically prevents these network outages from occurring, they have to make a conscious design choice. They must decide exactly how the system is allowed to react when it inevitably breaks. That choice comes down to two distinct survival strategies, mapped out here. When an error hits, the system can either throw up a hard blockade and immediately halt operations, or it can quietly route traffic around the broken component and keep moving. Make the wrong call, and you face one of two nightmares. You either permanently corrupt the underlying database with broken information, or you completely kill the user experience and leave your customers staring at a dead screen. System reliability isn't about building unbreakable code. It's about strategically drawing the lines of exactly where and how the software is allowed to break. Let's look at the first strategy, the fail-fast protocol. This is an intentional, immediate shutdown of a process designed specifically to protect absolute data correctness. Imagine you're transferring money between bank accounts. If the banking system detects a missing field or a slow connection halfway through the transfer, it cannot guess. Processing suspicious or incomplete data in this environment means real money disappears. If a request lacks an authentication token, the system doesn't try to work around it. It is instantly rejected and destroyed at the boundary layer. By crashing immediately, the software limits the blast radius, keeping the central storage vault perfectly intact. This approach aggressively sacrifices user convenience. The person on the other end gets a harsh error message and a blocked transaction, but the platform's availability is traded to guarantee absolute data integrity. In environments where truth is absolute, like handling payments or medical records, a loud, catastrophic-looking error is always safer than a quiet compromise. But what if you aren't moving money? If you're running a massive consumer application, a minor glitch in a background service shouldn't result in a total platform blackout. This is where we use the opposing strategy, graceful degradation. Here, continuous system availability takes priority over absolute correctness. Picture a global social media platform. Millions of people are scrolling. Suddenly, a server spike causes the recommendation engine, the part that suggests new accounts to follow, to time out. Looking at this network narc, you can see how the architecture isolates the failure. Instead of freezing the entire app, it disables that specific feature, dropping the suggestion box so the core feed of posts can continue loading seamlessly. The most sophisticated applications deploy both of these strategies simultaneously, using strict modular boundaries. Inside the exact same app, the payment processor is rigged to fail fast, while analytics trackers gracefully limp along. By isolating components that demand strict correctness, architects ensure that a critical failure in one corner doesn't infect the rest of the user experience. This architectural balance is becoming harder to maintain as more code is generated by AI. When an AI is prompted to fix a crash or ensure the app keeps running, it often optimizes for the path of least resistance. Often the AI wraps the failing logic in a generic try-catch block that simply swallows the error. On the surface, the app stops crashing, but because the catch block is empty, the system never reports that the data failed to save or the API call went unanswered. This creates silent rot. The UI looks perfectly healthy, but underneath, the database is slowly filling with incomplete records or missing updates that go unnoticed for months because no alarm was ever triggered. To avoid this trap, every network boundary must adhere to a definitive rule of error handling. Fail loudly and immediately for critical data. Fail gracefully and quietly for non-essential features. Armed with this matrix, you'll recognize these hidden decisions in every app you touch, from the checkout page that hard refreshes to the comment section that briefly disappears while your video keeps playing. The strongest digital systems aren't the ones that never break. They are the ones that know exactly when and how to fall apart. Thanks for watching, and join us next time as we dive deeper into the hidden mechanics of the web.